So, one of the things I want to focus on today, and we'll get to this in just a minute, is how to write a proof. So this is going to be how to write a mathematical proof. So how do you write a proof as opposed to, how do you think about why something should be true, right? And so this is like one of the important topics for this course. So, overall, I mean, there's a lot of important concepts that we will talk about, right? But some of the general things that we will learn is how to prove something, but also how to write a proper mathematical proof, right? And those things are a little bit different, and we'll talk about this in a minute. I also want to say that, so on the course information, the last page of the course, several people were asking about this. On the last page of course information, there's a notes. There's a notes for the class that I write, and I try to write them in advance, a couple of days in advance, and then I try to go over it the day, also to make sure to find typos and things like that. So that is more readable. So if I were you, I would first read the lecture notes that I post after the lectures. And then there's also on the last page of the course information, there is, and I try to do this in advance, but it's a little bit difficult to do it in advance. So it say the date, and it say some keywords from the lecture on that date. So over the weekend, I posted it for the 2 lectures for this week. But then I go back, I will try to go back, so I actually went back this morning and changed some of it from the second lecture so that it fits more. And I think I will only, I give references there to the book, and initially I was thinking of giving both references to Rudin and to the main textbook. I think it's probably just, I think it's probably smarter just to give it from the main textbook. Okay, but Rudin is a great book. This was a book that was created here long time ago, and it is like a classic in the subject. It's a great book. It's more formal than the other book. So the other book is a little bit more accessible. And so that's why we're using that. But actually, Rudin is a fantastic book. If it was just myself, I think Rudin is hard to beat. But the other one is more accessible, and so it might actually be better the first time you learn it. But so I think from here on out, so I deleted the references I had to Rudin. I think I would just give references to the main textbook, but I certainly encourage you to look at Rudin. Also, I also encourage you to look at chapters that we will skip, but there's also things that we initially skip and then we come back to. But again, you should, it's like when I list the things that we will cover in the lecture in advance, it's only sort of approximation, right? So once I write the lecture, it might be slightly different. Okay, so we had, so last time we talked about the theorem, we didn't prove it, that the reals is a complete ordered field. Right, and so in particular, it was an ordered set that was also a field, and it was complete, right? And so again, complete meant, so if you had a subset A here, which was a subset of R, then A is bounded bounded from above. If there exist M in R such that for all A in A here is less or equal to M. So, and then if that's the case, then we say that and M here is said to be an upper bound. For A. Likewise, if A here is a subset of R, then we say that A is bounded from below if there exist little m in R such that M here is less than A for all A. Okay. So this is upper and lower bound. Okay, and several people ask on Piazza, they ask, you know, they were a little unclear about you know, where does this M, capital M, where does this have to be? In what set does it have to be? And likewise for this little m, right? And so let me try to give you some example, and I try to do that on Piazza, but let me just because several people were asking about it, let me just say again. So that this capital M, when you have it like this capital M does not need to be in the set, right? A is bounded, so here's an example. If you're looking at the set 0, 1, so this is the interval, but it does not contain 0, and it does not contain 1, but it contains everything in between 0 and 1. This one here is bounded, so if this here is A, and we think about A here as a subset of R, then A is bounded. And so one usually say it's bounded if it's both from above and below. Right, so if one just say that it's bounded, then one means that it's bounded from above and below. It's bounded. And right, and so because like bounded from above, because you have that if x here is in this interval, then of course x is less or equal to 1, right? In fact, it's strictly less than 1, right? But you see, this set here, there is no element in this set that is an upper bound for this set, right? The upper bound is outside the set, but it is in all of R, and that's fine, right? An upper bound will typically just be in the larger set, and the same with lower bound. Now, everything on this board except this theorem, but you know this in terms of ordered sets, right? It has nothing to do, you know, it's just much more general than R. So if S here is an ordered set, and A here is a subset, So it's an ordered set. So it's a set with an ordering. And if A here is a subset of S, then again we can say that A is bounded from above. If there exists M, again M does not have to be in A, but it can be just in the larger set, so that for all A in A, it's less or equal to M. Right. So this is like the definition in general, being bounded above if you have an order set and you have a subset. Right. And now just to illustrate it, so typically we're going to think about where the set is R with the usual ordering, and you have a subset of it, and you talk about whether it's bounded from above or below. But of course, you could also do it in a more general setting like this, right? And so here's an example that if you look at, which maybe is counterintuitive, but if S here is the half line, so it's all the real numbers between say 0 and infinity. And then you would have A here is a subset 0 to 1. Fine. Now A here and the ordering. So this is of course a subset of R, but you should forget about R. I mean, you know the ordering from R, but forget about it because this is now what you think about the set S, right? And so if you're looking at A as a subset of this, then A here, A is bounded from above. Right? Why? This is just because for all A in A, you have that A here is strictly less than 1. So 1 here is an upper bound for A, right? But now think about, does this set here has a lower bound, right? Well, a lower bound have to be inside this set S, right? Because we're thinking about this here as a subset of this ordered set. We don't think about it as a subset of the real line. But if you think about it as a subset of this set here, then there is no lower bound, right? Because 0 is not in this set, and no negative numbers in this set. So this here, and this seems maybe a little bit counterintuitive, but A is not bounded from below. As a subset of S. Obviously, it is bounded from below if you were thinking about it as a subset of real line. But if you think about it as a subset of S, it's not bounded from below. Okay, so another person was asking the infinite and minus infinity. Those are not real numbers. Okay. Yep.
So on the homework, should we consider like all of the keys and stuff?
Sorry?
For like question 3 on the homework.
Yeah. If it's not directly stated that it's not directly stated that there's a set S, and then it has to be a subset of that set, right? Then it would be assumed that it's R. Yeah. Of course, you were welcome to to ask on Piazza. I don't have the homework here, but I would say that you're safe if it's not stated directly what the larger set is, then you can assume it's R, because we're going to concentrate mostly on R. This is another distinction between Rudin and this book that is the main textbook. Rudin is more abstract than the main textbook we are using. In particular, the main textbook here, and I'll do the same in my lectures, is that a lot of things are motivated from R, and then you abstract afterwards. So whereas Rudin starts with abstraction and then it specializes to R, and of course there's an argument for maybe starting with a familiar and then abstract instead of doing the other way around. Okay, so right, and so for whether it's just an ordered set, I mean, just in general, so remember that completeness. So completeness, so this is when you have an ordered set. So if you have an ordered set and A here is a subset of S that is bounded from above, then if it is complete, if S is complete, so if S is complete, then any subset that is bounded from above has a least upper bound. Then A has a least upper bound. Okay, and that least upper bound is denoted by the sup of A, right? So this thing here, it has the property that A is less or equal to M for all A in A, and also if M1 is another upper bound for A, then M is less or equal to M1. So that's a least upper bound. Right? And the same thing is, so similarly, when we have an ordered set, and we have a set if it's complete, and if we have if A here is bounded from below, then infer of A is the least upper, is the largest, the greatest lower bound. For A. Right, so this again means that this number here, little m, so m here is less or equal to A for all A in A. And if M1 here is another lower bound, then M1 here is less or equal to M. Right? So this is the symmetric property. And so again, R, the reals, is complete. So whenever you take a bounded subset of the real, so if it's bounded, that means that it's bounded from above and below, then it has a least upper bound and a greatest lower bound. Okay, and those are denoted by sup and inf, right? And in general, sup and inf are not in the set itself, in the set A, right? I mean, there could be, but in general, there wouldn't be. Yeah?
The example that we talked about earlier.
Yeah.
The open set.
Yeah. That's right. No, so if you're looking at this set here, right? So suppose that this here is the set S, then, and if you take A here, is a subset of S, and A here is bounded from, let's say that A here is bounded from below. Right? If it's bounded from below, then it couldn't be this set here. This here is not bounded from below, right? So it sort of means that if it's bounded from below, then A here could not have numbers that was approaching 0, right? And so actually, if it is bounded from below, if it's a subset of this and it's bounded from below, then actually it would have at least lower bound, greatest lower bound, right? You should mean. So it is. I mean, I'm not going to prove anything is complete or not complete, but it's pretty convincing that it is actually complete. Right? In this sense, there's another sense that is not complete, but anyway, in this sense, it is complete. Yeah. No, it's a little bit. It can be confusing. Later on, we'll talk about maybe some other notion of completeness, and then it's not complete. But in this notion, it is complete. Okay, so the next thing I want to get to is this with how to write a mathematical proof. Okay, and so and again, I mean that's a super important thing to learn in this class, and it's not just a formal thing. I mean, I mean, it may seem like a formal thing. Why bother with that? But it's really, really useful, and the more complicated things become, the more useful it is. And so I want to illustrate this with how to write a mathematical proof. So I'm going to illustrate this. So we will illustrate it by proving again by writing a formal proof of y square root of 2 is a real number. So I want to write, so last time we talked about that square root of 2 was a real number, but that when we proved it, it was more like we talked about the idea. And so then the question is, so if you have, like, you imagine you have a piece of scrap paper, what we did last time was what you would be writing on the scrap paper. So I want to talk about, if you were handing it in or showing it to somebody, then you wouldn't do that. You would do what we do now. Right? But it doesn't necessarily make for a formal proof doesn't necessarily make for a great lecture, because it's kind of formal. So let me try to explain how you should write this. And again, this is a very simple example, but hopefully it will give you an idea of what to do. And again, this is a really important part of this class that you're bound to use in many other classes later on. Okay, so let's first talk about what was square root of 2. So square root of 2, this here was a number, and it was given by that it has the property that it's positive, and when you square it, then you get 2, right? That was what square root of 2 was. Now, so we want to prove, so this is the theorem. So theorem, square root of 2 is a real number. So no, maybe I should write it more formally. There exists alpha greater than 0. There's alpha in R with alpha greater than 0, and alpha squared is equal to 2. Okay. Now we look at the set A. The set A is the numbers, it's the x such that x is positive, and x squared is less or equal to 2. Yeah, so x here. So now I was specialized to the real numbers. Okay, so that was why I didn't actually write it, but you're right. It certainly can't hurt. Okay, so that's the theorem. And so now we try to write a formal proof. Observe first that A here is non-empty since 1 is in A. Right? 1 is positive, and when you square 1, you get 1, so this is definitely less or equal to 2. So A here is non-empty. Next, observe that A here is bounded. It's bounded from above. In general, by the way, when you write a proof, then you really only try to establish the properties that you need, because otherwise it's confusing. If you establish all kind of other property that is not needed, that just makes it confusing. So it's bounded from above. And this is just because since 2 is an upper bound. For A. Okay. Now the next thing is, so now we have a non-empty bounded subset. So we set alpha equal to the suit of A. And we want to show that alpha is positive and alpha squared is equal to 2. Well, right, by definition, the way we defined A, all the elements in A were positive. So by definition, 0 is a lower bound. So you for sure have that 0 here is less or equal to, well, it's actually, I mean, even 1 is a lower bound. So you can also just say that 1, since 1 is a lower bound, since 1 here is in A, you also have that this alpha here must be bigger or equal to 1. Right? Because it was supposed to be an upper bound for A, so in particular. Now, and so we have that alpha is less than 1, and it's the least upper bound, and 2 was an upper bound, so you have this. Since maybe I should write, if you write it with this, since 1 is an A, we have that 1 here less or equal to alpha. And since alpha is the least upper bound, and 2 is an upper bound, we have that alpha is less or equal to 2. Okay, now remember, I mean, we're going to do it exactly like we did last time, but we're just going to write it down in a proper way as a proof. Right, so remember that last time we then divided the proof into 2 steps. The first step was so part 1. So all we need to prove, maybe I'll just say that, all we need to prove to show is that alpha squared is equal to 2, right? Because we already have it as positive now, because it's bigger than 1, right? And so there was 2 parts to this, to step 1 and step 2, or part 1 and part 2. The first part was, so part 1, we will show that alpha squared is less or equal to 2. Right. And so we prove this, so assume not we will show that that leads that this leads to a contradiction to that alpha is the least upper bound. For E. I mean, I'm writing everything out here, right, just to illustrate it, right? As you get more and more familiar with this, right, then the structure is the same, but, you know, some of these steps will seem almost too trivial, and that's probably fine, right? But, of course, it's always good to err on more details than fewer details. Okay, so this is what we want to do. So we assume not, so assume that alpha squared is strictly bigger than 2, right? Then, and this is where it sort of deviated more from how we did it last time. And that's why, you know, what we did last time is really what you want to have on the scrap paper. I mean, that's what we did last time was like the idea And then once you see the idea, then you try to write it as a formal proof, like what we do now. And so assume not set h equal to, so I'm going to set h equal to alpha squared minus 2 over 4 alpha. Okay. Right. Obviously, if this was like the first time you would do it, you wouldn't just come up with this sort of thing, right? I mean, this is coming from the scrap paper that you have, right? So you're setting h equal to that. And then you observe that since alpha here is bigger than 1 and alpha squared is bigger than 2, since that, right, then the numerator here is positive and the denominator is positive. So h here is positive, right? You also have that h is right. You also have automatically that that h is, maybe we don't need that. Let's see if we need that. So okay. So now you set alpha 1 equal to alpha minus h. And what I want to prove is, so we want to show that alpha here, alpha 1, is an upper bound. For A. So I want to prove that this is an upper bound for A.